Hi, everybody. I know this format is a little bit different than how we normally meet, so I want to say that I appreciate your patience while I try to get figured out how I'm going to deliver content online. For now, this is my setup. You can see me in the corner, and then you can also see what I'll be working on, just like you would look at the whiteboard. So I'm going to go ahead and get started. So we're going to talk about S.12, which is radicals. Hopefully most of this stuff will be a review for you guys. If you need more review, remember, you can always look at the links that are in the video links module for our regular Canvas page. There is a video already posted about radicals, and I will post another video soon up there from Professor Simpson's YouTube channel that also has to do with radicals. Okay, so if you feel like this isn't enough of a review, that is always an option for you guys. The other thing about the new format is if you can't hear me or you can't see what I'm doing, make sure to let me know sooner rather than later so that I can fix the formatting of the video so that everyone can see what I'm doing and hear what we're talking about. Okay, so the first thing I want to do with radicals is remind you of how the notation works. Okay, so if you have an expression that looks like this, okay, remember the entire expression is called a radical. Okay, so the whole thing is a radical expression. Okay, and then the pieces of this have different names. Okay, so n is called the index. Okay, and remember that tells you what type of radical it is. So if there's no index, it's a square root. If there's a 3, it's a cube root, etc. Okay, and then a is called the radicand. Okay, so the inside stuff is called the radicand. Okay, so let's look at first simplifying radicals. So if we're going to simplify radicals, which I think you guys should be super familiar with, we have to agree on what makes a radical simplified. Okay, so this stuff is outlined in the supplement if you read this section of the supplement, but I will also tell you now. Okay, so okay, let's talk about the things that would make a radical simplified. Okay, so the first thing, and this is kind of what you see the most with square roots, is that you don't want any factors inside the radicand that could be rooted. Okay, so the radicand should have no factors with an exponent greater than the index. Okay, so you don't want that because you could pull those factors out, right? If you have x cubed, that's a perfect cube. You want to remove that from the radicand. Okay, the second thing that you need for something to be simplified is the radicand has a positive coefficient. Okay, so we talked about I in our last class period after the exam. So you know if you have a square root with a negative in it, you need to change it into the complex number form. Okay, so that is really why that rule is in place. Okay, you also want that the radicand doesn't have a fraction in it. Oops. Okay. And then the last real rule that we're going to follow is that the index is reduced as much as possible. Okay, now this is something that might be new to you guys, so we will talk about how to do that and why you would want to do that. Okay, but the last thing, and this is something that they talk about in the supplement, we've talked about this in class a little bit, how this might not be super important in every situation. Okay, so I'll put this one in parentheses to show that this is not always something we're worried about. Okay, but it does include it, and we are going to talk about it, that the denominator has no radical. Okay. All right. So when we get to that, I'll talk about what situations that make sense and why you might want to do that. Okay, but for now, I just want to include that in the times that something is simplified. Okay, so let's do a couple examples. Okay, so the first thing we're going to do is we're just going to simplify. Okay, and I want to do a review example first. So we'll do a simplify example that is a square root. Okay, now because you guys took Algebra 2, you should be familiar with this, okay, but I do want to do an example of the technique that I use to simplify. Okay, so what I use is I always split this into two pieces. You want to split it into the part that is a perfect square, okay, and then you want to split it into the part that is left over. Okay, so you're looking for a factor of 75, okay, that is a perfect square. So we know 75 is 25 times 3. Okay, so I'm going to put 25 as my perfect square part. Okay, and then 3 would be my leftover factor. Okay, then I'm going to look for factors of x to the 5th that are perfect squares, and I wanted to remind you that it is even powers that are perfect squares. Okay, so we'll have x to the 4th, and there's one x left over. Okay, and then for y to the 7th, we would have y to the 6th as our perfect square, and there's one y left over. Okay, so now we're actually going to split this up. Okay. Okay, and then we're going to evaluate the left part because this part comes out evenly. Okay, so we're going to take the square root for this. So the square root of 25 is 5. The square root of x to the 4th is x squared, and the square root of y to the 6th is y cubed. Okay, so we're actually taking the square root of that part because it comes out evenly, and then the leftover components, okay, are just there in the square root. Okay, all right. So I can't really ask you if you have any questions. That's one thing that's different about this formatting than our other format. So make sure that you're attending the Confer Zoom sessions if you do have any questions, or that you're using office hours and SI session. Okay, so let's go ahead and do another example. Okay, and now we're going to do an example that's a cube root. Okay. Okay, now the real difference between the square root example and the cube root example is now we're looking not for factors that are perfect squares, but for factors that are perfect cubes. Okay, so we're looking for a factor of 16 that's a perfect cube. Okay, so you might think, oh, 16 is divisible by 2, so I'm going to look maybe 2 times 2 times 2, or 2 cubed, right? That would be 8. Okay, and then our leftover part would be 2, right? Because 8 times 2 is 16. Okay, then similarly to what we were doing before, when we said that even powers are perfect squares, it is powers that are divisible by 3 that are perfect cubes. Okay, so we would have x to the 6th, and then we'll have one x left over. Y to the 12th is divisible by 3, so we'll leave that. Okay, no y's left over. And then for z, we'll have z cubed is a perfect cube, and we'll have z squared left over. Okay. All right, so again, we're going to split this up. So here's my perfect cube part, 8x to the 6th, y to the 12th, z cubed. okay? And then my leftover parts, which are 2xz squared, okay? All right, so now I'm going to take the cube root of this part that comes out evenly. So the cube root of 8 is 2, the cube root of x to the 6th is x squared, the cube root of y to the 12th is y to the 4th, and the cube root of z cubed is z, okay? And then I still have this part, 2xz squared, okay? All right, so that's all I'm going to do of these kind of review examples. Like I said, I think you should be familiar with this. So let's move on to a slightly more complicated example. I do want to look at something that has a fraction just so that we're all familiar with how to evaluate those. Okay. All right. So we're going to use a cube root example again because, like I said, I think that's more the level of this class versus Algebra 2. Okay. Okay. So the first thing you look for when you are actually simplifying a fraction is you want to simplify the radicand or the inside part before you do anything with the square root. Okay, so the first thing we're going to do is reduce this fraction as much as possible. Okay, so then we would have x to the 7th over x. We know that's x to the 6th. Okay, and then that would leave us with 2y in the denominator. Okay, so once we've reduced the fraction as much as you can, then we're going to use the property of radicals that you can split the radical into the numerator and the denominator. Okay, and then we're going to simplify either of these if it's possible. Okay, so this one comes out evenly. The cube root of x to the 6th is x squared. Okay, and there's no way to simplify this radical in the denominator. Okay. All right. So I wanted to talk a little bit about when you should and when you shouldn't rationalize the denominator. Okay, so here I think you don't need to, because if you look at the denominator and the numerator, there are no common factors, okay, first of all. And second of all, the directions aren't specifically asking you to rationalize the denominator. So unless the directions specifically ask, you really only need to do that when you have something where the denominator and the numerator are going to have a common factor that you're trying to cancel out. Okay. All right. So that's all of the simplify examples that I think should be reviewed. Okay. So let's look at reducing the index. Okay. Okay, so even though the directions say simplify, remember part of simplifying is that you are reducing the index as small as possible. Okay, that was one of the rules that we saw for fully reduced radicals. Okay, so let's look at an example. Okay, so we have the 6th root of x squared. Now you can't simplify this by taking out any powers of x, right? Because the exponent here is smaller than the index, okay? So you can't use traditional simplification methods to simplify that. Now, I wanted to remind you guys, okay, that these radicals are also related to fractional exponents. So remember that this is really equal to, sorry, this is x squared. Okay, this is really the same as x to the 2 over 6. Okay, now you guys know you can reduce these fractional exponents, right? So we could rewrite this as x to the 1/3. Okay, now we're going to mimic that process without actually having to change into the exponential form. Okay, so if you look at this expression, you can see that the exponent 2 and the index 6 have a common factor of 2. Okay, so we're going to reduce by the common factor. okay, which is 2. Okay, so we're going to divide the index by 2 and get 3, and then we're going to divide the exponent by 2 and get 1. Okay, so this is the same as what we saw using the fractional exponents, okay, and this is just a way to do this without converting to exponential form. Okay, so let's look at one more example of this. Okay, so we're looking for the greatest common factor between the exponents and the index. Okay, so you can see that the greatest common factor for 2, 6, and 4 is 2. So we're going to reduce everything by 2. Okay. Okay, so when you divide the index by 2, right? 4 divided by 2 is 2. Now, do you ever put the index 2 here? Not really, right? Because the standard notation is to leave out the index when it's a square root. So we're not going to put a 2 here because we don't need to, okay? But that is the index. It's going from 4 to 2. Now this exponent is going to go from 2 to 1, okay? And again, you don't need to write x to the 1 power. And then here we'll go from y to the 6 to y cubed. Okay? So that's how you can reduce the index. Okay? So hopefully that's kind of a new topic for you guys. Okay? So let's move on to operations with radicals. Okay? So before we do that, let's talk about what it means for radicals to be like terms. I just want to remind you. Okay? So radicals are like terms. Okay. Now it's a very specific set of conditions. They have to have the same index. Okay. And the same radicand. Okay, so let's look at a couple examples of things that are like terms and then some stuff that are not like terms. Okay, so these ones are like terms. Okay, so you might have something like root 2x, okay, and then -6 root 2x. Okay, these both have index 2. They're both square roots, okay, and they also both have the radicand 2x. Okay, you might have something like cube root of 6xy, okay, and then 5 cube root of 6xy, okay. So these are like terms. So let's look at some examples of things that are not like terms, okay. Okay, so we're going to look for things that are not like terms, but they may seem like they're like terms. Okay, so if you have something like 2 root x, okay, and then you have 2 root y, those are not like terms. So even though they have the same coefficient, they have different radicands, which makes them not the same. Okay, then if you have square root of x and cube root of x, okay, those are not like terms either. They have to have the same index, and these two have different indices. Okay, and the last thing is the radicand has to be exactly the same. So even if you have cube root of 2x and cube root of 2x squared, okay, these are not like terms. The radicand has to be exactly the same. Okay, so let's use that information to go ahead and add and subtract some radicals. Okay. Okay, So we're just going to add and subtract some radicals. Okay, so let's look at an example with a square root that I think should be a review type example for you guys. Okay, so if you look at this right now, they both have square roots, but they're not like terms because they have two different radicals. Okay, so you can't add root 75 and root 12 in this form. Okay, they're not like terms. So what we need to do is look at each of these and see if we can maybe reduce them and hope that they'll become like terms. Okay, now there's no guarantee that that would happen, but we do want to give that a try. Okay, so 75 we can write as 25 times 3. Okay, and then 12 we could write as 4 times 3, right? Remember, you're splitting up into perfect square part, leftover part, perfect square part, leftover part. Okay, so root 25 is 5, root 4 is 2, okay? And now you can see that you do have like terms, which allows you to add them together, okay? So this would leave you with 7 root 3 as your final answer. Okay, so let's do a slightly more complicated example. Okay, actually, I'm going to leave it at that for the adding and subtracting, just in an effort to keep the video as short as possible. Let's look at an example of multiplication. Okay, so the thing about multiplication is the same principle that you use to simplify radicals, you can use to split up radicals. Okay, so we have been using the idea of separating the square root, but we're going to do the opposite of that and take the multiplication of two roots. Okay, so let's see a review type example. Okay, so we're going to multiply these by multiplying the radicands together. Okay, so 9 times 6 is 54. X squared times x squared is x to the 4th. Y times y to the 4th is y to the 5th. Okay, so that's the step that is actually the multiplication. You just multiply the two radicands together. Okay, so what we're going to do now is we're going to try to simplify our answer. Okay, so we're looking for perfect cubes. So something that's a perfect cube that divides 54. Okay, so you may not think of it right away, and if you don't, okay, this is what I would do to look for perfect cubes. Okay, so the reason we got this is because it's 9 times 6. Okay, and you can see here, there's your perfect cube. Okay, so we would have 27 and our leftover component 2. Okay, x cubed and 1 more x, y cubed, and 2 y's left over. Okay, so then we're going to take the cube root of our perfect cube part. That would leave us with 3xy. And then our leftover component is 2xy squared. Okay. So most of the difficulty of the multiplication is coming from simplifying. When you're multiplying, you are just multiplying the two radicands together. Okay. All right, so let's do a more complicated one of these. Let's talk about distribution. Okay. Okay, so you're going to multiply these the same way that you would multiply any binomial, by distributing. Okay, so we're going to distribute the first term here to these two terms, and then we'll distribute this term here to these two terms. Okay, so we would have 4 root 2 times negative root 2. Okay, then we would have 4 root 2 times 3 root 3. okay? Then we'll have negative root 3 times negative root 2, okay? And the last term is going to be negative root 3 times 3 root 3, okay? All right. So let's simplify each of these, okay? So you're going to do each of these by multiplying the radicands, okay? So we'll have negative 4 root 4, okay, plus 12 root 6, okay? Minus times minus is plus, so we'll have plus root 6, okay? And then my last term, I'm going to have negative 3 root 9, okay? Now you don't really need to write out this middle step here if you're comfortable with this. That was just to explain where each of these terms is coming from. But for you guys, if you're comfortable, just go straight from the question to this step here. Okay, so now I'm going to simplify. Root 4 is 2, so this will give me negative 8. Okay, and root 9 is 3, so I'll have negative 9 here from 3 times 3. Okay, so now I'm going to combine my like terms, so negative 8 and negative 9 is negative 17, okay, and 12 root 6 plus 1 root 6 is 13 root 6. Okay, all right, so that's enough for multiplication. So before we talk about division, let's talk a little bit about the technique that we use to divide, okay. Now we talked about this before in class. We talked about radical conjugates. Okay. So radical conjugates, remember, have the same terms. With opposite sign between. Okay. Okay, so some examples of this would be 1 plus root 2. The radical conjugate is 1 minus root 2. Okay, if you have two radicals like root 2 minus root 3, then the radical conjugate would be root 2 plus root 3. Okay, so same terms, opposite sign in between. Okay, so what we use this for is for division or for rationalizing the denominator. Okay, so let's do a couple examples of this. Okay. Okay, so I'm going to put explicitly in the directions that we're meant to rationalize the denominator, okay? And I will normally do this because, as we've been talking about in class, I think they overemphasize rationalizing the denominator in certain classes, so I will explicitly tell you, okay? And the only other time you would need to is if you are looking for something that has like terms, and we'll do an example of that, okay? So let's look at something where we're going to use okay, radical conjugates. Okay, so you guys can see here that both the numerator and the denominator are rational expressions. Now, if you want to rationalize the denominator, you're going to use the conjugate of the denominator. Okay, so our conjugate for the denominator is root 3 minus root 2. Okay, and then because we multiplied by that in the denominator, we need to do the same thing in the numerator. Okay, and now we're just going to distribute and multiply this out. Okay, so 1 times root 3 is root 3. 1 times negative root 2 is negative root 2. Okay, then negative root 2 times root 3 is negative root 6. Okay, and negative root 2 times negative root 2 is positive root 4. Okay, all right. In the denominator, root 3 times root 3 is root 9. Root 3 times negative root 3, negative root 2 is negative root 6. This is going to give me positive root 6. Okay, and then for the last term, I'll get minus root 4. Okay, now this is the important feature of this method. If you look at what's happening here with these two terms, those two are going to cancel out. And that's the point of this method. When you use conjugates, you are always trying to get rid of what's called the cross terms, which are these two terms from the multiplication. Okay, so if you're using the correct conjugate, these two terms will always cancel out. Okay. So in the numerator, the only thing we can do is this root 4 can become a 2. So we'll have root 3 minus root 2 minus root 6 plus 2. Okay, and then in the denominator, okay, root 9 is 3. These two terms are going to cancel as we discussed, and this root 4 is 2. Okay, so 3 minus 2, of course, is 1. Okay, and then we don't need to put over 1, right? So this would be our final answer. Okay, all right. So that's an example of how you can use the conjugate method to get a rational expression in the denominator where you aren't having a radical at all. Okay, so if you have something in the denominator that only has a single term, like this, okay, so then you want to, the only time for me that I would want to rationalize the denominator is when I see that there are common factors in the denominator and the numerator. And that's certainly the case here because I have y and y, but I also have 2 and 4 here. Okay, so by rationalizing this, I think I'm actually going to be able to simplify and cancel some common factors. Okay, so what I want to multiply by here is something that's going to make this a perfect square. Okay, when you multiply. So I need, if I have one factor of 2, if I multiply it by another 2, I know I'll have a perfect square, right? 2 squared. And same with y. If I multiply by y, I know I'll have a perfect square. Okay, and then I'm going to do exactly the same in the numerator. Okay, so here I'm going to multiply straight across. I'll get 4x root 2y squared. And then in the denominator, I'll have root 2y times root 2y, which is root 4y squared. Okay, so remember this is the point of this method. You can see that here in the denominator you are getting something that's a perfect square. Okay, so in the numerator we're going to be able to simplify this root y squared to give me 4xy root 2. Okay, and then in the denominator everything should simplify out of the square root. That's the goal in this method, and you would have 2y. Okay, now we're not done at this point because as was our objective, right, we have some common factors here that we can cancel out. Okay, so 4 divided by 2 is 2. We still have our x, and then y divided by y is 1. Okay, so we'll just get 2x, right, these are canceling, and then root 2. Okay, all right, so let's expand on that idea a little bit and use that same method, but with a cube root. Okay, oops, that's not what I wanted to do. Okay, so you can see here that we definitely have some common factors that we want to cancel, and that explains why we might be, oh, I still can't enumerate just like we're in class. Okay, so this explains why you might be interested in rationalizing the denominator. You're definitely going to be able to cancel some things here, here, and here. Okay, so just like the previous example, what we're looking to multiply by is something that's going to give us a perfect cube. okay? So I have one factor of 3 here. I need 2 factors of 3 here to make a perfect cube, okay? I have 2 factors of x. I only need 1 more to have 3. I have 1 factor of y, which means I need 2 more to make a perfect cube. Okay, and then I'm going to mirror that in the numerator. So I'll have 3 squared x y squared. Okay. All right, so now I'm going to multiply straight across. Okay, and in the denominator, right, I'm going to multiply my 2 radicands. So 3 times 9 is 27. Okay, x squared times x is x cubed. Y times y squared is y cubed. Okay, and you can see, just like you wanted, everything in the denominator is a perfect cube, and that's the goal. Okay, so I'll have my numerator exactly the same. Okay, and my denominator, I'm going to take the cube root. Okay, so cube root of 27 is 3, cube root of x cubed is x, cube root of y cubed is y. Okay, and now I'm going to be able to cancel. So I have this 3 in this one, this x in this one, this y in this one, and I would just end up with cube root of 9xy squared. Okay, so that's the case that I think that rationalizing the denominator is the most useful, and when I would naturally recommend doing it is if the directions explicitly specify that, or if you have these common factors, like you can see in the original problem, you know you want to be able to cancel these, but because of the radical, you can't. Okay? All right, so I'm going to wrap it up there. Those are the examples that I wanted to go over with you guys. If you go to our Canvas page and look in the worksheets and solutions module, you will see a worksheet corresponding to S.12 that I posted there for you guys. You do need to complete that. That replaces the classwork that we would have done in groups in class together. Okay, and unfortunately, because we can't meet, we can't do any group work, please complete that. You can ask questions about it during either my office hours or our ConferZoom session, or Jacob's SI session that will also be through ConferZoom. So you guys are expected to complete that, although you won't be turning it in. Okay, so please go and take a look at that now. And if you have any questions, please contact me. Okay, bye.